Hello and welcome to part 3 of TensorFlow tutorial for beginners video series. In previous part, we basically implemented a plain vanilla neural network for MNIST fashion dataset by flattening out the images. But for images, it is recommended mostly whenever possible when you have huge amount of data to exploit the convolutional neural network rather than plain vanilla neural network. So in this particular video, we are going to solve exactly the same problem, fashion MNIST dataset, classifying fashion MNIST images using convolutional neural network rather than plain vanilla neural network. But it should be noticed that even using convolutional neural network, at the very end when the features are computed, you have to deploy ordinary neural network or plain neural network to eventually classifying any kind of images. So what these convolutional and pooling layer does, they actually extract salient features that are very fruitful. They actually exploit the spatial structure of the images to extract features that are very handy and salient and discriminative in terms of classification and other machine learning tasks. So in this particular video, we are going to deploy these convolutional layers and the pooling layers. Normally this convolutional and pooling layer combined is called a convolutional layer, and this is a convolutional layer. The pooling is not just max pooling. You can have average pooling, and there are other ways of pooling. The kernel normally is the size of the window that actually slides over and computed features for you. So yeah, let's dive in to the Google Colab, and let's see first the code for the previous problem we solved with the ordinary neural network, and let's convert that code. We will be generating a new notebook, but mostly we will be copying pasting the code that we did, and we'll be changing the cell that requires actually convolutional neural network part. So let's go to Google Colab and see that's our original neural network. We imported TensorFlow, we import the data, and then actually after checking certain shape of the data in the last video, that's our model that we train, the neural network model, where we have a flattened layer at the top, then we have certain layers, we have certain dropouts, and we used Adam optimizer, sparse categorical cross entropy loss, and accuracy model. So that's mostly our model that we did in the last video. In this particular video, deploying convolutional neural network, we have to actually change this particular cell mostly. We have to add some convolutional layer on top of these, or maybe changing the structure of this. And also we have to define the shape of our training data as well as test data into a form that convolutional neural network can accept. So mostly these are the two cells that will be changing, with a little bit change in the rest of the things. Everything else will stay the same. So let's actually convert this notebook to a convolutional neural network notebook. Let's first generate a new notebook, this one. So yeah, it's generating a new notebook. Yeah, it's ready. Let's rename it. Let's name it like model CNN. Let's say this convolutional neural network model. First of all, let's import TensorFlow as TF. It will obviously allocate, initialize, and connect to the server, and will give us some resources. This will be done very first time when we'll execute the code. Now everything is running, at least everything that we need, that is running. Now what we do is we just copy and paste some of the data from the previous notebook, and here we go. We download the data. If you're not in Google Colab, if you are working on a PC, if you have downloaded data at once, if you run this command again and again, it will not go to the internet and download. It will actually pick that data from the cached copy you have. Next, we go back to our previous notebook. We have a shape like this. We have 60,000 images. Each image is 28 by 28. That's why training and stuff like so. This is important thing that we need. So let's copy this here. The class names. Let's define the class names. Yeah, they are defined. Now, after that, we basically move to this normalization. But before normalization, we actually have to define the structure of this data that actually is required for convolutional neural network. The convolutional neural network, when it takes images, it actually takes in the form that the very first it takes an ND array where the very first dimension represents the number of images, and the rest of the dimensions that actually represents the size or the dimension of images itself. So for that, what we do is we convert that into that particular form, xtr training dot reshape, and what we do here is the following. We pick the very first thing, xtr dot shape 0, that will give us the total number of images, and we reshape everything with the total number of images times the dimension of one image. So the one image is 28 by 28 by 1, and this actually represents the total number of images. So that converts in a form that the neural network, the convolutional neural network layers, they're happy with. So we do the same with test data dot reshape. So xtst dot shape 0, and then we have the size of each image 28 by 28 by 1. So yeah, so and these are the scalings. It's always good to have the scalings. I mean, the feature scaling is important in most of the cases, and it is required. This is not the only way to scale the features, but this is one way, easy way, and it works most of the time. So yeah, it works very fine. Next, we move to our model. Now everything is set. Now this is our model. Let's copy and paste this, and here, there, and let's see what can we do with that. So now that's our model. Let's call this model as CNN model. Let's have a CNN model that is sequential. These are the layers. Here we have to actually, if you go back to before actually applying this neural network, we have to apply these convolutional layers to actually extract the features, and this neural network at the end which will actually take care of the classification for that. So let's extract certain features by deploying some convolutional layers. So what I do is df.keras.layers.conv2d, conv2d, that's a layer. In this conv2d, I have to first define the total number of channels or filters. Let's say we have 32 filters. What's the size of each filter? That's hyperparameter. Again, let's 3 by 3. That's the size of the filter. And what's the input shape that it is expecting? This is for the very first time. Input shape, and that is equal to the input shape. The input of our image is 28 by 28 by 1. So that's the convolution layer that is added. Below the convolutional layer, we may have a max pooling layer or some pooling layer. tf.keras.layers.max pooling 2D, two-dimensional pooling. And here we have to define basically the size of the pooling. So let's say 2 by 2. We can have, for example, we can have a dropout below it. We can have multiple convolutional layers. For example, we can have another convolutional layer here, or maybe a dropout layer here. Either way, I mean, the architecture really is a hyperparameter, how to define that. Layers.conv2d. And again, we can have the number of filters. Let's say the number of filters here is again 32, or you may have more or less number of filters. The size of each filter here. the size of each filter. Here the size of the filter, you can have a 3x3 filter, or you can have I mean, either way. Here you need not to define the shape of the input because that is required for the very first time. Then we have this tf.keras.layers dot maybe max pooling layer again, 2D, yeah. And here you have to give the size of the pooling. And after defining this convolutional structure, here I have added just 2 convolutional layers, each layer followed by a max pooling layer. After defining that, you have to flatten your input just like previously, but you need not to give the input dimensions here because that will be defined automatically. And then you have to define the structure that you really want for the rest of the network. One more thing, you can have a dense layer here, and then you can follow the then you can convert that to probability model, or you can directly have a dense layer along with the activation as softmax, and then your model will be directly ready for predictions. So activation is equal to, for example, softmax, yeah. So that's your model. I mean, you can change the model, but that's how you can define a model for a convolutional neural network. Let's run it and hope that it works fine. Yeah, it's perfectly okay. Next, what we do is we actually compile our model. So CNN model is equal dot compile, and here we have to define our optimizer, our loss, our matrix. We can change, we can, I mean, we can have a lot of choices here. So optimizer, let's say the optimizer is Adam again. The loss, let's say loss is categorical cross entropy, categorical cross entropy. And the metric that we are going to define is, let's say, the accuracy matrix. So is, let's say, accuracy. We can define multiple matrices here. That's why it receives a list. So accuracy. So that's the metric. Let's compile our model. If it works fine, yeah. And then we fit our model. So CNN model dot fit, and it receives XTR. Now this YTR actually should be given here for this particular case. It should be given after converting it to categorical form. That's a one-hot encoding that is required. So let's convert that. tf.keras.utils to categorical, and let's convert this YTR to categorical. Here we have to define the number of epochs. So epochs, let's say, is let's say 10, and if everything is fine, the model should run. So let's see, yeah, the epochs are running. It will take some time, and the reason is these convolutional layers and the pooling layers, they are actually expensive. So yeah, it is taking time, I guess a lot of time. Let's wait until it finishes. Okay, so now epoch 2 is running now. We have to wait until it finishes. So that's the third epoch. One thing that you might notice here, the loss, as the number of epochs go more and more, the loss should decrease, and the accuracy, it should increase or at least stay there. So yeah, it's fourth epoch now. It may take a few minutes now. Maybe I should pause the video, and once all the 10 epochs they are over, I should come back then, just to not increase the length of the video. So let me pause the video and come back then after all these epochs they're done. Okay, so we are done here with 10 epochs, and here you can notice the loss actually gradually goes down, and the accuracy actually gradually goes up. Care must be taken. You may tend to increase the number of epochs just to increase the accuracy and decrease the loss, but then there might be a problem of overfitting. Although you have cared about overfitting here in dropout, there are other ways of getting workaround with overfitting, like early stopping and stuff like so. So these are set of techniques that must be taken care of. So after this, the rest of the story is exactly the same. Now our model is trained. We have to predict. So let's predict. Y predict is basically CNN model dot predict. Remember here we deployed this softmax layer directly inside the model. So we need not to convert that to probability model separately. In the previous video, we actually converted the previous model to the probability model explicitly after applying the softmax layer by not deploying the softmax layer in the last layer. Here we actually have deployed the softmax layer inside, so the probability model is already there. So we directly call the predict function. And we predict this on xtest. So xtst, hopefully it should predict. So it is making predictions. So it may take, yeah, so predictions are ready. Next, we test some of our, the performance of our model on some of the testing examples. So let's say I is equal to, let's say 100, class label is, let's say, np.arg. Oh, we haven't loaded np, so let's load np here. Import numpy as np. So yeah, so that will work. So np.arg max y predict I. So that's our class label. So and here we print basically the class name for this class label, and then we actually print the actual label. So print actual label cn y tst of I. So yeah, so the actual label will be printed below and the predicted label will be printed on top for the ith example. So let's see. Okay, so we predicted dress and the actual label was dress. So let's play with that. Let's go for 20 and run this. The actual label is pullover. Oh, we predicted pullover and the actual label is also pullover. So we can go to, for example, some other value, maybe 50 or something, or maybe we generated this value randomly and run overall. So far we are doing very well. Yeah. So let's say we have some random, maybe np.random.rand int maybe, and we may generate that rand int by the length of ytr test. That will give us some random integer, and for that let's check ankle boot. Let's generate again something randomly, again ankle boot, pullover code. Oh, that's the first mistake that we found right now. The actual label is quote, and we classified, our model classified it as pullover. Let's run it again and see. Dress code, yeah, it's working almost fine. Again, I mean, this is not a good way to test the accuracy. This is just eyeballing how it is performing. But that's what the overall structure is. So what we have learned so far is that the convolutional neural network is really simple to implement in TensorFlow just by adding some convolutional layers and pooling layers, maybe some dropouts inside. And the rest of the story is exactly the same as you have seen earlier. One difference is that you have to set your dimensions of your array consistent with the spatial structure that the convolutional neural network actually requires. So yeah, that's about it. In this particular video series, we basically introduce the reader, the beginner, the viewer to TensorFlow and give a couple of examples to quickly implement neural networks and convolutional neural networks in TensorFlow. But TensorFlow is much more than that. You can actually have recurrent neural networks. You can do encoder-decoder networks. You can do dimensionality reduction. You can build generative adversarial networks here in TensorFlow and much more. There are visualizations using TensorBoard, and I mean the TensorFlow is a whole kind of I would say it's a whole universe. I mean, for deep learning, if you explore this more and more, you will get more and more fruitful features of it. So this particular video was intended to the very beginner and was supposed to give a quick start for TensorFlow. Even if you don't know how to install TensorFlow, just go to Google Colab and just write your network and you're ready to go. So that's it. If you like our content, please press the like button, subscribe our channel and share this video. Yeah, hope to see you next time.